In this video, we will look at number 30 and number 36. In number 30, and I've included your graph in the study guide just to speed things along for you, but when you are doing these problems, you should follow the directions in the order they're given. That is, state the power and constant of variation, then graph, and it even uses the word then to emphasize that in the directions. So our constant of variation, which is k, in this problem is -2, and our power is -3. So the first thing I would recommend you do before you study too hard on how to evaluate or analyze this graph is to notice that anytime the exponent is negative, you can rewrite the function as the coefficient or constant of variation as your numerator, and then move the power into the denominator, and then it makes perfect sense when you see the graph that it looks so much like the parent graph. And the parent of all graphs that are functions that look like this one is the 1 over x graph, which would look something like this in the first quadrant, and then would be reflected in the third quadrant. So it also should make sense when you see it from this perspective that the graph is in a vertical reflection of the parent graph because of the -2. The 2 would be a stretch, and cubing the denominator, which would really be cubing 1 over x, is going to not change the overall shape of the graph. And I'd be happy to discuss that with you in more detail if you are curious and interested, but that's not necessary to finish this problem. So let's go down the list of things we are to analyze for this graph. Our domain starts at -infinity, and then as we're moving from the left, we see a vertical asymptote at 0, which means you're going to exclude 0, and then close with positive infinity. Then go to your range, which starts at the bottom at -infinity, and again we move up until we see a horizontal asymptote at 0, and then we exclude 0 from our range as well. And then when you're asked about whether a function is continuous, it's good if you understand that this is a continuous function because the only place it has a discontinuity is outside its domain. But we would be telling really more valuable information if we were to say we have, in fact, I'm not going to use the word discontinuity, I'm just going to say we have a non-removable vertical asymptote, or as your book would call it, an infinite discontinuity at x equals 0. And if you think about it, if I told you that a function had a vertical asymptote at x equals 0, that would tell you a lot more than if I said, yeah, it's a continuous function, because it's continuous on its domain. So if we go to the next question, which is increasing, decreasing, if you start at the left and then move to the right, and I'll trace what I'm saying as I say it. So if I start at the left of this graph and trace it the whole time, even though right here it feels like you're going horizontal, you're really creeping up very slowly the whole time that you're moving from left to right. And then when you jump the asymptote and come to the other side, then you are creeping up not creeping up, but you're flying up initially, and then you creep up very slowly forever. So at all times, you are going up. So from left to right, which is how you should always analyze increasing, decreasing, this function increases on its domain. Which also tells you that on intervals, you could argue that the further you are to the right, the larger the output of the function. And then the next question you want to think about is the symmetry, and obviously from the graph, it's odd, but we would go a step further, and some practice we clearly need based on our performance on the must-know function test on Friday. We need to demonstrate, prove our answer correct by saying f of negative x equals negative 2 over negative x cubed, which would then be negative 2 over negative times a negative times a negative is still negative x cubed. So I can write the same thing without the parentheses, and then the negatives cancel off and leave me 2 over x cubed, which is the same thing as what we started with except the opposite sign. So that tells us that f of negative x equals negative f of x, so the function is odd. And then we are to talk about whether the function is bounded, and since there's no maximums or minimums or anything of the sort, no, not even local ones, we can say it is unbounded. And we'll kind of answer two questions at once here by saying unbounded, semicolon, no extrema. And then asymptotes we've already alluded to, at least in different contexts. So we will, in fact, I won't write the word asymptotes here, it's already on your paper. We have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And then for our end behavior, we want to look at what the graph is doing as we go out to the end. So let me erase all this other stuff off our graph so that we can look at what we're talking about here. And at the ends is what we're looking at for these two. So the way we write that is the limit as x approaches negative infinity of f of x. And that says what we're about to state, the meaning of what we're about to state. Well, if you think about it, the further I go to the left on this graph, the smaller the output will be, and it will head towards but never get to 0, because this function can never be 0. Well, then when I go out to the right side, I have the exact same scenario, the only difference being that I'm coming towards that limit from the bottom, but we don't care when we're talking about limits how we're getting there. We just care that there is one or not. So now we are going the limit as x approaches infinity of f of x, and that also equals 0. And it is permissible for you to write those two statements as one when the limit is the same in both directions. And I'll move over into this empty space here and write this as a more compact statement and say that the limit as x approaches plus or minus infinity of f of x equals 0. And that is the only acceptable way to write a limit statement from this point forward in the course. Prior to now, I've been pretty lenient with how you express your limit statements. I've even let you kind of intermingle symbols and words, but from now on, this is what I expect. Alright, number 36, which will be the only other one I do on this video with you, is from a different problem set. And this one says, describe how to obtain the graph of f of x from the parent function g of x equals x to the 7. And then state whether it's even or odd, sketch the graph by hand, and verify your graph by graphing it on your calculator. And again, it is important that you follow the order of these directions. So the first thing is our description. And remember, to describe these changes, all we have to do is to look for what's different in the equation we're given and the parent function. And in this case, our parent function is x to the 7th. And the only difference is that 1/8. It's an outside multiplier less than 1. So this is a vertical shrink by 1/8. That is the only difference between and you could be more explicit here, I guess, if we go ahead and say of x to the 7th. So then we're to state whether the function is even or odd, and we're not just going to write the word. We're going to prove that we're right by writing f of negative x equals 1/8 times negative x to the 7th, and then we figure out how to drop the parentheses and rewrite it correctly. Well, I'm going to put the 1/8 here, and one of two things will happen when you do these problems. You'll either change the sign of your coefficient or you'll keep it. So if you leave yourself a little room, that makes it okay either way. Well, a negative raised to any odd power is still negative, so I can rewrite this by putting the negative out front and writing this as x to the 7th. So this is the opposite of what I started with, and the way I denote that is I say f of negative x equals negative f of x, so the function is odd. That tells me that when I graph this, I know I will have diagonal symmetry in my quadrants, and because this is x to the 7th, by this point you should understand that that should give us a graph that looks a lot like the most common, commonly studied, I guess, function of an odd power, and that would be x cubed. So we're going to plot these points on the graph, and as we would with any power of x, we're going to start with 0, and 0 squared, cubed, whatever is 0, but in this case it's 0 to the 7th, but that's still 0. And if we were graphing the parent function, we would do 1 to the 7th, which would be 1, but this one is a vertical shrink, so I'm going to go to the right one and up an eighth. Well, you're not going to have to be super precision here with that, but you want to graph that point as close to the x-axis as you can, probably for 1/8 because it's going to be such a tiny fraction. And then we would go to the left and down by the same amount. Well, if you go to 2 steps out, we run into a bit of a problem because 2 to the 7th would be 1/28, and even though we get to divide that by 8, which is 16, we still don't have enough room to graph that here. So we're going to use our knowledge of how this function should behave similar to a cubic and just run it on out. And you want to make sure that your graph is, as it moves out, it's up, it's going to continue to go out. And you're not at any point going anywhere vertical. And I was doing that really slow, so it was getting wobbly, so let me do a little better job. And it should still be pointing outward, even if it's a very subtle outward motion. And I would honestly rather you exaggerate that a little bit and go a little too wide than to risk going vertical or turning back in on the ends of your polynomials. Alright, we're going to stop this video here and pick back up with one more video to close out our examples for section 2.2.